So given these differences in the methods, the definition of extreme and the framing of the questions matters. So depending on how the model's attribution studies is carried out, the questions answered can be very different. For example, how has the frequency and magnitude of this class of extreme events occurring changed over the past X decades? Here you are looking at comparing an extreme event in one period, and instead of making a full counterfactual simulation and producing statistics and looking for statistical property changes and attribution of drivers, attribution to drivers, you're just taking a period that is in the past where you have made some assumption about the impact of humans on that climate, and you are comparing to another period where the extreme event occurred. So you are just looking for the change over the past X decades. For example, when somebody says monsoon extremes, widespread monsoon extremes have become 3 times as frequent as before, they are just looking at the trend in the widespread extreme rainfall in the last several decades and just saying the frequency has changed. You can do the same for rainfall events greater than 150 millimeter per day, and you can do it for cyclones, how number of cyclones has changed over the last however many decades for which you have data, and so on. So that's not exactly attribution, but it does give you a sense of the relation between changing of ocean temperature or land temperature or deforestation, urbanization, any kind of a variable that you consider a driver for a particular event, that class of events that you are looking for, and it concludes some link in terms of attribution. Given all other the other question answered could be, given all other conditions being equal, how has the risk of such an extreme event occurring changed as a result of anthropogenic emissions? So in this case, you could be doing just the simulation with and without emissions. So you could be removing aerosols, you could be removing CO2, you could be removing all greenhouse gases for a particular event, and assume that the natural variability is similar to before, and so on, and just say that the risk of such an event has changed because now the CO2 levels are different than before. So this is not a full-blown counterfactual world simulation. This is just taking the same year simulation or same event simulation, but just changing the greenhouse gases and aerosols to some other period. Could be all the way back to pre-industrial, or could be just beginning of the 20th century. Some judicious choice has to be made to claim the attribution. Other ways to make decade-long simulations and look at this way, the question being, given all predictable long-term things being equal, so you look at decadal timescales, how has the risk changed due to the global mean temperature increase and increase in greenhouse gas forcing? This tends to be somewhat more robust in the sense that the year-to-year variability can confound El Nino and internal variability, seasonal variability. For example, the winters in mid-latitudes typically tend to be more variable in particular climate variables like temperature, snowfall, precipitation, winds, whatever. So the detecting trend in winter could be harder in terms of separating forced variability versus anthropogenic variability. So the risk change also has to will also become difficult. But making let's say decadal change in winters will give you a better sense. Okay. approximately. I hope I explained it okay. The other way is to make short-term predictions and look at the question, given all predictable short-term conditions being equal, how has the risk of such an extreme event occurring changed as a result of anthropogenic emission? Okay, so just the point is that this is a reference 10 from the paper. Each one has a reference, but somehow I didn't delete this one. Anyway, the question that is being answered depends on how the modeling framework is set up and how the attribution is framed. So you can look at the example here. So we are looking at temperature, return time in years, and looking at actual ensemble for 2000 to 2010 decadal simulation, and a particular year like 2005 actual ensemble, and then the same periods 2000 to 2010 counterfactual ensemble and 2005 counterfactual ensemble. So return periods of daily minimum temperatures in July in East Africa in 4 different ensembles. Remember, it's their winter. The graph shows July minimum temperatures in the actual climate simulation of the year 2005 in magenta here, and the decade of 2000 to 2010 in the actual climate, so it's the actual 21st century simulation, and July minimum temperatures in the counterfactual climate simulation of the year 2005 and 2000 to 2010. What does it mean? Basically, you go back in time and find the CO2 levels which correspond to no human impact, and then you try to simulate the same set of let's say initial conditions, and then these simulations of a particular year or a particular decade, trying to capture internal variability of the same year. 2005 was probably ENSO neutral year, for example, and it would have had a phase of NAO and PDO and so on and so forth. Those are internal variabilities. So horizontal dashed gray line represents the threshold of 19 degrees centigrade. The arrows represent the increase in risk. So we are looking at the decadal change. So you are going from the bluish line here for the decade, from counterfactual world to the factual world, actual ensemble. That is the change in the return period for this minimum for the risk of exceeding this minimum temperature threshold. So that has gone from about let's say 3 or 4 years to much less than a year here. Okay, so every season it could be happening. If you look at the particular year 2005, then 2005 in the counterfactual ensemble had the risk of return period of more than 10 years, and it has been reduced to less than 1 year. So in a season you could have multiple dips in minimum daily minimum temperature below 19 degrees centigrade. Okay, so that's how you would do the interpretation. Why look at short term and long term? I thought I could use this example to say, if you look at the global mean temperature trends with respect to the base period 1951 to 1980, you see that the temperatures were below this base period when you go before about 1940. Then temperatures began to jump around, and then we have gotten into this rapid and monotonic warming. But there are ups and downs still, because you still have natural variability, and the energy is going to melting glaciers and so on and so forth. And we keep saying 2016 was the all-term warm record in the instrumental period. 2020 tied the record, I think, and the warmest top 5 years have been in the last few years, and so on. But this says that looking at year-to-year changes can be problematic, because natural variability is always confounding the trends. But if you look decade to decade, so if you look at the decades of 1890s, 1910s, 30s, 50s, and so on, you can clearly see that once you got into the anthropogenic era of clear human impacts, each decade has been warmer than the previous decade. Okay, that's not so obvious here, but climate change is a kind of a slow, low frequency change, and weather happens within that climate envelope. So you have to understand how particular events that would happen anyway are being modulated by the warming. This is the main question of attribution. Okay, so I hope it's clear why the framing of the extremes question is very critical, and based on the framing, different approaches are used and different timescale simulations are used, but the questions answered are also different. So each attribution study has to then clearly specify what question they were trying to answer, what extreme they were looking at it, and what the definition of the extreme was, and what were the perturbations done to the simulations to extract the drivers and the conclusions and the narrative about the risk change and so on and so forth. Okay, so the framing is very critical.